Good morning, everybody. Today, I am going to present to you the topic of thermodynamics of gas liquefaction. Okay. Now, the basic things what we are going to talk about is the concept of matter, the kinetic theory of gases, Avogadro's law, Dalton's law of partial pressures, the concepts of internal energy, enthalpy, and entropy, and then work done under various processes, the specific heats, then the distinction between ideal and real gases, the thermodynamics. Then we'll move on to the topic of thermodynamics, starting with the zeroth law of thermodynamics. First, we'll define the thermodynamic systems and so on. Then we'll talk about the zeroth law of thermodynamics, the first and second law of thermodynamics, the concepts of heat engine and refrigerator, the efficiency and COP, that is coefficient of performance, the concept of entropy, and also try to see if we can solve one or two problems in this area. So this is going to be the presentation format of my present lecture. Okay, matter exists in three states, namely solid, liquid, and gas. The solid melts to a liquid, and then liquid vaporized to a gas. And similarly, gas condenses into a liquid, and liquid freezes to a solid. Now, the atomic theory by John Dalton makes sure that all things are made up of atoms. And we also see that when the chemical compounds are formed, there are some standard laws which are followed. The first law is any given compound has a fixed proportion by mass of its constituents. That is sodium chloride or silver chloride, for example. 1 unit of sodium combines with 1 unit of chlorine. Similarly, 1 unit of silver combines with 1 unit of chlorine. Another law which we come across is when two elements form to form more than one compound, then a fixed mass of one element. For a fixed mass of one element, the other masses are the ratio of small integers. For example, you take like copper sulfate. If you take copper sulfate, copper 2 units, sulfur 1 unit, and oxygen 4 units form the copper sulfate compound. We come across Gay-Lussac's law. The Gay-Lussac's law says when gases combine chemically to yield another gas, their volumes are in the ratio of small integers. Okay, for example, ammonia. 1 unit of ammonia combines with 3 units of hydrogen. Okay. Avogadro's law is another important law which we have to consider. Italian scientist Amedeo Avogadro, 1776 to 1856, he suggested that all gases occupy the same volume under the conditions of same temperature and pressure, and they have the same number of molecules. Okay. This number is known as Avogadro number, and I think this number is 1.6023 into 10 to the power 23 is the numbers. Okay. Now we come across the size of the atom. The size of the atom is approximately about an angstrom. Then angstrom will be about 10 to the power minus 10 meters. Solids are tightly packed. Atoms are spaced a few angstroms apart in a solid, or some maybe 2 to 3 angstroms. But in the liquid also, it's about the same. But in the liquid, this long range order is not there. Short range order is the present. In gases, there are interatomic distances which are tens of angstroms. Okay, this is what you find. Now, the average distance between the collisions of gas molecules, you call them at mean free path. What you notice is a gas state is full of activity, and the gas is in what you call the dynamic equilibrium. The molecules collide and they change their speeds during the collisions. Various properties such as pressure, volume, temperature, or assigned to the gas, and you can consider them as average properties of a gas. Now, these are sometimes known as thermodynamic variables, and there are also other thermodynamic variables which will be describing the state of the gas. So we will come back to this at the time when we discuss about thermodynamics. Let us come to ideal gas. The ideal gas, this we have seen in the earlier lecture also. In the ideal gas, it says it is the equation of state for a dilute gas, and it is can be written as pressure into volume is equal to the number of moles multiplied by R, which is the universal gas constant, into T, the absolute temperature. Okay. Here, P is the pressure, N is the number of moles of gas, T is the temperature in Kelvin, and R is the gas constant, which has the same value of for all gases. That's why you call it as universal gas constant. And you can also define what is called, you can rewrite the above equation as, say, for example, if you take 1 mole of gas, then N will be equal to 1. So you can write it as PV is equal to RT. So R can be rewritten as N into K, where K is the Boltzmann's constant, N represents the Avogadro number of molecules. Because we know that equal volumes of all gases under the same conditions of temperature, pressure contain the same number of molecules, and the same number of molecules nothing but Avogadro number. So K is equal to R by Na, which is, so you can substitute 8.31 joule per mole Kelvin divided by 6.023 into the power 23 per mole, which is equal to 1.38 into the power minus 23 joule per Kelvin. So this is the Boltzmann constant. It represents the R value per molecule. Now let's come to the kinetic theory of gases. Kinetic theory is very useful in describing the gas phase at high temperatures. So it is assumed that the molecules are in random motion, and for an ideal gas, they are point masses, there is no volume. The motions are random and instantaneous, and there will be collisions that will be happening between the molecules, but there is no loss of energy by collisions, and there is no mutual force of interaction between the gas molecules. So this microscopic picture of this gas can lead to the macroscopic behavior, and we can try to understand what is the behavior in the macroscopic condition. Let's try to understand pressure, derive an expression for pressure based on this kinetic theory. So for that, pressure is caused by the collisions of molecule on the surface of a container. Okay. Now, to arrive at an expression for the pressure, let us consider a unit cube, that is 1 centimeter by 1 centimeter by 1 centimeter, a unit cube. Okay. Consider a single molecule in this, and let us say it's moving only in the x-axis and its velocity is u. So if the velocity is u and the number of collisions that will happen per second will be equal to u. Okay, the mass of the molecule is m, and therefore the momentum of the molecule will be equal to mu. And what will be the change in momentum per collision? It will be mu minus mu, because it will go and collide and return back at the same direction backwards, and therefore it is minus mu will be the change, the momentum while it is returning. So the change in momentum will be equal to 2 times mu. Now the rate of change of momentum is the number of the total momentum change per second. But we know very well that the number of collisions are u, and therefore the rate of change of momentum will be equal to the change in momentum multiplied by the number of collisions per second. So it is equal to 2 mu into u, which is 2 mu square. This actually happens on 2 walls, because the molecule goes and collides on one side, comes back and collides on the opposite side. And therefore, it is happening in 2 walls. So the collision, the momentum change on per wall will be equal to mu square, 2 mu square by 2, which is mu square. Now, we made an assumption that there is only one molecule in the system. It's not true. There are n molecules which are present in a particular volume V. Now the change in momentum per second would be equal to, then, so that is the number of molecules that will be present in this will be equal to N by V, number of molecules per unit volume will be unit cube. So N by V into mu square. Okay, another important assumption is that the molecule moves only in the x-axis, which is incorrect. The molecule has an average velocity, let's say V, italics V, and 1/3 of the gas molecules will be in the x direction, 1/3 will be in the y direction, 1/3 will be in the z direction. Therefore, we have to consider this. So we have to write is now, instead of writing N by V mu square, you have to write it as 1/3 N by V mv square. Or if you cross multiply, we can write pressure into volume is equal to 1/3 nmv square. This is something important. So the pressure, the expression pressure is equal to 1/3 N by V, 1/3 into N by V into mv square. Okay. Now the product of pressure into volume is 1/3 nmv square. By ideal gas law, PV is nothing but RT. In other words, we can write it as N into K into T. So NKT is equal to 1/3 nmv square, or you can rewrite it as half mv square is equal to 3 by 2 kT. You can simplify and show that half mv square is equal to 3 by 2 kT. What does it show? It shows half mv square is the kinetic energy of per molecule, and this kinetic energy is directly dependent only on temperature. Okay, depends only on the temperature. That's what you see. Okay. Now, this is for the case of an ideal gas. Okay. Now the in the left-hand side, V is the volume of 1 mole of gas, and N is the Avogadro number. N is already, we have defined it as Avogadro number. So what we see is this is known as Joule's law. Half mv square 3 by 2 kT refers to Joule's law, which says kinetic energy is directly proportional to absolute temperature, which is known as Joule's law. But for real gases, it will depend also on other thermodynamic variables, not necessarily only on temperature. Maybe it will depend on pressure, etc. Okay. We can calculate an expression, calculate the value of R by a simple, by considering these data. For oxygen, density is 1.429 so many grams per liter. And in other words, specific volume will be volume per gram is divided by 1 by 0.001429. Pressure will be 76 centimeters of mercury, and temperature is 273 Kelvin. So R can be written as PV by T. Then we can write 76 into 13.6 into 981 divided by 0.001429 into 273, which is 2.605 into 10 to the power 6. The units will be ergs per Kelvin per gram. Oxygen has a molar mass of 32 grams, and therefore if you take 1 mole of oxygen, you have to multiply by 32, and if you multiply this, you get 8.34 into 10 to the power 7, so many ergs per Kelvin per mole. So this, since 10 to the power 7 ergs will be equal to 1 joule, it will be 8.34 joules, okay, per Kelvin per mole. Or if you want to write it in terms of the calorie units, it is 1.987 calories per Kelvin per gram. This R is known as the universal gas constant for all the gases. Now, Avogadro's law says equal volumes of all gases under the same conditions of temperature and pressure have the same number of molecules. This can be proved by using this above equations. So we can write, for example, suppose we have a gas molecule A and a gas molecule B. They have the same pressure and temperature, which means now product of pressure into volume has to be same for both of them. So 1/3 Na Ma Va square should be equal to 1/3 Np Mb Bb square. Since we already know half Ma Va square is equal to half Mb Bb square, because the temperature is the same. So this kinetic energies have to be the same. So if you substitute this in this above equation, you find Na should be equal to Nb. That means the molecules, number of molecules have to be the same in both for both cases. Okay. Now the Dalton's law of partial pressure also can be proved by this process. It says PA, PB, PC, PD are the pressures of the gas when they occupy the volume V. Let's say the partial pressure is PA, PB, PC, and PD. The total pressure is P. Now, since the number of molecules have to be, total number of molecules should be equal to Na plus Nb plus Nc plus Nd equal to N. So we can write total pressure is equal to Na plus Nb plus Nc plus Nd into RT. You have to multiply this by divided by pressure is into RT by V. So you get, I think there is a mistake, small mistake here. Anyway, it doesn't matter. We'll write P is equal to NART by V, NBRT plus NBRT by V plus NCRT by V plus NDRT by V, which is nothing but PA plus PB plus PC plus PD. So that means the total pressure is nothing but the sum of all the partial pressures of this gas molecule. Now we introduce the concept of kinetic energy. Kinetic energy is the sum of the internal energy is the sum of all the kinetic energies and the potential energy of the molecules. This is known as the internal energy and is designated by the term U. In the case of a polyatomic molecules, kinetic energy will also include the rotational and vibrational energies other than the just a translational kinetic energy. The internal energy can also add additionally this information. So we can write, say, U is equal to summation of half mv square, approximately equal to summation 3 by 2 kT. So if you rewrite this in terms of RT, then you can write 3 by 2 N times RT, because the number of molecules should be N. If you sum over all the number of molecules, then it will be N into R into T. Okay, that will be the, N will be the number of moles. So N into R into T in this case. So what we notice is the internal energy is only a function of temperature for the ideal gases. But for real gases, it can be a function of pressure, temperature, or volume and temperature. Let us introduce the concept of enthalpy and entropy. Now, the total energy of the gas arising out of its pressure and volume and the internal energy due to the temperature T, and this total energy is given by H. H will be equal to U plus PV. U is the internal energy, P is the pressure, and V is the volume. The product of pressure into volume is also an energy term, and therefore the energy, total energy, that is inclusive of the internal energy, is known as the enthalpy. Okay. At a given temperature, if a small quantity of heat is added to your system, then we say the entropy changes. Now, entropy is defined in different ways. It is also taken as the disorder of the system, a measure of the disorder of the system. Now, we can say the change in the entropy, in this case, if a heat is added to your system, it is ds is equal to dq by t. Normally, entropy is treated as a disorder of the system. For a reversible cyclic process, entropy change is zero, or in other words, ds is equal to zero. And to get an idea of the entropy, normally tables are prepared, and these tables are such that the entropy value is assumed to be zero at 0 Kelvin. Okay. And for the preparation of all these tables. Okay. Now let's understand the work done by a gas or on the gas. What is the work done? The work done is given by force into displacement. Now, let's consider the figure on the right-hand side, on the topmost figure. So you have a piston in an initial state represented by dotted lines. The gas is trapped here. Now, the gas is now trying to expand. When it expands, it pushes the piston upwards, and the piston goes to a final position as is shown here. Let's say the cross-sectional area is A, and it has moved over a distance of dl, delta L. Okay, so we'll try to find out what is the work done. The work done is given by the formula force into displacement. Force is nothing but pressure into area. Okay, area over which the force is applying. So into now displacement, which is delta L. Pressure into area, pressure into area. So area into delta L will correspond to the change in the volume. And therefore, you can rewrite this as work done is equal to pressure into change in the volume. If you consider infinitesimal work, it is P into dV. Now, this is okay as far as the fact that if you have a very, very small change in the delta L, but in case the system undergoes from an initial state P1, V1 to a final state P2, V2 as shown in the diagram below, then you find the work done has to be integrated over the initial state to the final state, and therefore W should be equal to integral V1 V1 to V2 PdV, which is nothing but the area under this curve, area under the P versus V curve. Okay. Now, there are sign conventions. The sign convention is if the work is done by a gas, it is taken as positive, whereas if the work is done on the gas, it is taken as negative. Okay, there are different thermodynamic processes, and I am representing some of these processes. Okay, for example, if the temperature is constant, it is called an isothermal process. For an isothermal process, you will find the n value will be equal to 1. Because we are always writing P V to the power n is equal to constant, and n will be equal to 1 because the isothermal process. For an adiabatic process, n will be equal to gamma, okay, or it's also known as isentropic process. Here the entropy is kept constant, and therefore it is an isentropic process, and that for which n is equal to gamma. Now, for a constant pressure process, which is known as isobaric process, n will be equal to 0, and for a constant volume process, which is an isochoric process, n will be equal to infinity. Enthalpy process will be, constant enthalpy processes will be somewhat different. They are known as isenthalpic process. Now you can represent the processes either in the PV diagram or in a TS diagram. In the PV diagram, what you see here is pressure is actually on the y-axis and volume is on the x-axis. So isobaric process will be a constant horizontal line. Isochoric process will be a constant vertical line. Isothermal and isentropic will have processes which are inclined like this, but isentropic will be having a higher slope compared to the isothermal. The same thing can be represented also in the TS diagram, and you can see isothermal is horizontal line, isentropic is a vertical line, and similarly isochoric and isobaric process are inclined like this, and isenthalpic process also is shown here. Okay. Okay, now if you want to calculate the work done in isochoric and isobaric processes, the work done for a constant pressure process will be integral PdV equal to P into V2 minus V1, because the pressure remaining constant, volume changes, so it is nothing but the area under the curve. If you consider a constant volume process, integral PdV will be equal to 0 because the volume does not change in this case. Okay, there are expressions for isothermal adiabatic process where in which PV is equal to constant in the case of isothermal process, and PV is equal to N or gamma, okay, in the case of isentropic process. So there are expressions available for this. For example, for isothermal process, it is W12 is equal to P1 V1 ln V2 by V1, or P1 V1 ln P1 by P2. Similarly, for isentropic process, it is W12 will be equal to P1 V1 by n minus 1 into 1 minus P2 by P1 to the power n minus 1 by n. And if you replace n by gamma, it becomes isentropic process. If you just retain it as n, it is becoming a polytropic process. Okay. Now let's come to the specific heat of a gas. In the case of a gas, what is specific heat? First, let us try to understand what is specific heat. The heat energy required to raise the temperature of the substance by unit degree, unit mass of substance by unit degree is the specific heat. Okay. And now the heat capacity is nothing but the overall mass is getting raised by 1 degree centigrade or 1 degree Kelvin. Then that is called the heat capacity. So heat capacity can be defined as delta Q by delta T, where delta Q is the heat supplied to a substance to change its temperature from an initial value of T to T plus delta T. Okay. Now, specific heat capacity will be that for unit mass or 1 by m into delta Q by delta T. Okay. What are the units? It is so many joules per kilogram per Kelvin. Now, in the case of solids, normally they are at constant pressure. Solids or liquids, and therefore you have only one specific heat, namely specific heat at constant pressure. In the case of gas, there are two variables possible. Either the gas can be at constant pressure or at constant volume. So you have two different specific heats, namely specific heat at constant volume and specific heat at constant pressure. Okay, and the ratio Cp by Cv is called the ratio of specific heats. And for monoatomic gases, this ratio works out to be approximately 1.6. Okay. Right. Let's move on to the next topic. Let's talk about the behavior of gases. Now, real gases behave differently compared to ideal gases. The real gases, the difference between the two gases is real gases have a finite volume for the gas molecules, and there is also interaction energy between the gas molecules. So the permanent gases such as nitrogen, oxygen, argon, hydrogen, helium, they behave similar to ideal gas at high temperatures and low pressures. Whereas as you decrease the temperature, they start behaving differently than the ideal gas. Now the expression for real gas can be given by van der Waals equation of state, which can be written as P plus A by V square into V minus P is equal to RT. The first term, A by V square, shows that there is an additional interaction energy because of the mutual interaction between the gas molecules. And V minus V represents there is a reduction in the volume because of the finite size of the gas molecules. Now, Avogadro's experiments on carbon dioxide show us the real behavior of real gases. Now, this we have seen also in the earlier lecture. As you keep on decreasing the temperature of a gas, then there is in the PV diagram you find that there is an inflection point, and that inflection point indicates that the liquefaction of gas is now possible below this particular temperature. Okay. So this inflection point is known as the critical temperature. It's also followed by a critical pressure, okay, below which only the liquid state of the gas exists. So at a point A, if you consider gas at point A, it is a saturated vapor, and by compression, it becomes a saturated liquid. It becomes a saturated vapor and ready to liquefy at the point B. And then B to C is a constant pressure process where the vapor continuously condenses and becomes a liquid. And then once at point C entirely, it becomes a liquid. And further compression leads to only sharp rise in the pressure of the liquid because liquid becomes incompressible. Now, the critical temperatures of a few gases are given here. Oxygen is at 154 Kelvin at a 50.1 bar pressure. For nitrogen, it is 126 Kelvin at 33.5 bar. And for hydrogen, it is 33.2 Kelvin at a pressure of 12.98 bar. And helium, 5.2 Kelvin at a pressure of 2.26 bar. Okay. Now, clearly, below the critical temperature, the liquid state of the gas exists. And therefore, if I want to convert a gas into a liquid, I need to bring the temperature down below the critical temperature. Now, the diagrams which indicate the pressure versus temperature for a typical gas is known as the phase diagram. In the phase diagram, you will very clearly see the states of the substance, namely the solid, liquid, and gas. When all the three lines, solid to liquid, will be the fusion curve, and liquid to vapor will be the vaporization curve, and solid to gas will be the sublimation curve. And the point at which all the three lines meet is known as the triple point, which shows the coexisting of all the three states. Okay. Now, you can also see in the case of solid carbon dioxide at 1 bar pressure, the solid goes directly from solid to vapor. That means it undergoes sublimation. So, the physical state of a substance is defined by the pressure and temperature around it, or in other words, it is depicted by the phase diagram of the substance. Okay. Now, the TS diagrams are all available for real gases, and you can notice that, as I already mentioned, that for obtaining these TS diagrams, you normally assume that at the entropy of the gas molecules are zero, the empirical gases are zero at absolute zero of temperature, and then you can plot these things for either constant enthalpy curves or constant density curves or constant pressure curves can be plotted on this one along with the saturation zone of typical gas. Okay. Okay. Now let's move on to the thermodynamics. First of all, what is thermodynamics? It is a science of energy that concerned with the ways in which energy is stored in the body. Thermodynamics originate from two Greek words, namely therm and dynamic, which indicates heat, and the dynamic situation of gas molecules, okay, are the effects of the force on the gas molecule. Now, there are energy transformations that can happen within the gas molecules, and it can involve the heat as well as work that is carried out by the gas. Okay. But basically, the fundamental law is the conservation of energy, and namely, energy cannot be created nor destroyed, but only it can be transformed from one state to another. Right. Let us define a system surrounding and the boundary. A system is a quantity of matter, okay, or a region in the space chosen for our study. Surroundings is the mass or region that is outside the system. What is boundary? Boundary is the real or imaginary surface that separates the system from the surroundings. So you can see here the system and the surroundings and the boundary. Right. Now we can define different type of systems. An isolated system in which neither mass nor energy can cross the selected boundary, right? Okay. And isolated systems are all ideal, but in any case, we can consider the ideal system. In this, neither the energy nor the mass can cross the boundary. As an example, very approximate example could be a coffee in a closed, highly insulated thermos bottle so that the temperature doesn't change and the mass also is not modified. We can think of closed systems wherein the energy can cross the boundary, but not the mass. Okay, so that such a system is called closed system. We can think of a tightly capped cup of coffee, but as you can see, after some time, the coffee will become cold. So because the energy transfer is taking place from the surroundings, from the coffee to the surroundings, and therefore the coffee will become cold. You can think of the other system, which is called the open system. In the open system, you have both mass and energy can cross the selected boundary. Maybe just an open cup of coffee. If you think of it, it is wherein the coffee, the water vapor will go out, as well as the temperature will drop for the coffee with the time. Okay. So, for example, typically you can consider a heat exchanger in which there are fluid flows happening, a cold fluid entering from one end and becoming hot at the other end, and similarly hot fluid entering at another end, opposite end, and becoming cold in the opposite direction. So such a system can be considered as an open system where both the energy as well as mass happen. Now we can define certain properties of the system. One of the properties is called the intensive property, another a property called extensive property. Intensive properties are those which are independent of the amount of mass, such as, for example, temperature, pressure, density, etc. Whereas extensive property means it depends on the mass. Okay. So we can think of intensive properties like temperature, pressure, density, etc. Whereas extensive property could be the mass, volume, things like that. Okay. There are properties related to that. Okay. There are specific properties. The word specific indicates that it is per unit mass, and therefore these are intensive properties. And you can see there are a number of properties can be considered: specific volume, density, total energy, internal energy, enthalpy, entropy, specific heat, ideal gas constant. All these things refer to the intensive properties. Okay. So the expressions are given here. Okay, for each one of them, you can just go through that. Now let's come to the laws of thermodynamics. First, we'll talk about the zeroth law of thermodynamics. If any two bodies on equilibrium, thermal equilibrium with the third body, then all the three bodies are in equilibrium with each other. That's all it says. Suppose we consider A is in equilibrium with the T, thermal equilibrium with the T, and B is also in thermal equilibrium with the T. A, B, C are in thermal equilibrium with each other. What is thermal equilibrium? Which means temperature is the same and remains constant in time. So this is depicted in this picture. What you can see, that's your zeroth law of thermodynamics. What is the implication of this? Is the system always tries to tend towards thermal equilibrium. So suppose a system is having high temperature and kept in an environment which is at low temperature, then the temperature will go down. Similarly, if the system is at a low temperature and it is kept, it's actually, you are bringing it to, keeping it room temperature, then it will warm up and come back to room temperature. If the system is having the same temperature as the environment, the temperature is not going to change, it will be the same. Okay. So this is all it means by this process. Now let's come to the first law of thermodynamics. It says, the first law is usually referred to as the law of conservation of energy. Energy can neither be created nor destroyed, but gets transformed from one state to another. Okay. So suppose I add a certain quantity of heat into the system, it goes to two purposes. One is it changes the internal energy of the system and then performs some external work. Okay, and therefore, if dQ is equal to du plus dW, dQ is the heat input in the system, du is the change in internal energy, dW is the work output of the system. Now, there are some sign conventions which people always follow. dQ is supposed to be positive, is taken as positive when the heat is added to the system, and is taken as negative when the heat is removed from the system. So these are the conventions. Okay. We can think of different processes. I will just go through the various processes which I have in mind. The adiabatic process, it is a process which occurs on a system that is well insulated and there is no transfer of thermal energy occurs between the system and the environment. Okay, now what we can do is we can put dQ as 0. In the above expression, dQ is equal to du plus dW. And if you put dQ is equal to 0, you can write du is equal to minus dW or dW is equal to minus du. Either way. So what does it mean? It means, suppose gas is piston cylinder arrangement is isolated from the surroundings and suddenly the gas is made to perform work. And then the working of the gas will now, the energy has to come from the gas itself. So its internal energy decreases and therefore gas temperature drops. Similarly, when a gas is compressed, suddenly then the energy goes into the gas and raises its temperature. So dQ is equal to 0 and therefore du, change in energy, will be equal to the negative of the work done by the process. In a constant volume process, obviously there cannot be any work and therefore dW is equal to 0. Whatever heat input you are giving in, it goes to the change in internal energy. Therefore dQ is equal to du. For a cyclic process, internal energy change will be equal to 0. That is, the gas goes from one state to another and comes back to the same position. And therefore, du is equal to 0, which means dq is equal to dw. It's very, very important to know that by adding heat into the system, we can generate some amount of work done. We can generate certain work in this process, in the process. Okay, the addition or removal of heat into the system can create or create some work into the work performed by the working fluid. For a free expansion, dq and dw is equal to 0. Here there is no work done by on a piston, and because of which du also will be equal to 0. This process is known as free expansion. We'll discuss it at some later time. Coming to second law of thermodynamics, first we get a concept of an engine. What we notice is that work can be performed by a gas, and therefore this gas, we'll call it as the working fluid. By combining several processes in the form of a cycle, we notice that we can extract work from the working fluid along with a heat source. So you add some heat, okay, and you go through the cycle of operations, come back, and thereby you will be able to produce certain amount of work by the gas. Now this working fluid, along with the addition of heat, okay, is actually forming a concept of engine, an engine. And what is an engine? Engine is nothing but a gas undergoing a cycle of operations such that it comes back to always its initial state. So what we can do is since it is taking heat as the input for its working, we call it as a heat engine. And this heat engine can now be used to produce work. Question is, can we convert 100% of heat into work? No. This is because heat energy is not as good as the other forms of energy. Sometimes it is called low-grade energy, which may be or may not be right. But the second law is the one which tells you that such a thing is possible. This diagram shows you, for example, a gas can be made to perform work, and you can see there is a net result of the work done in the process. Say, for example, here, if I take from I to F, this is the amount of work done, okay? And in this case, the work is greater than 0. That means there's a positive work done. You take this particular diagram in which you start from F and then go back to I, then in that case, work is less than 0, which means work is done, okay, on the gas. In one case, work is done by the gas, the other case, work is done on the gas. If suppose I take a state from I to F and initial state to final state, and then go back in the opposite direction, but in a slightly different modified path, there is a net work output done, which is nothing but the work in the area within the two curves. Okay. So in other words, by taking a gas through a cyclic process, it is possible to make sure that the gas performs some work. Okay. Now let's come to the second law of thermodynamics. It says there are two statements of second law of thermodynamics exist. Kelvin-Planck statement. Okay. It says no process is possible whose sole result is the absorption of heat from a reservoir and the complete conversion of heat into work. In other words, no heat engine can have a thermal efficiency of 100%. In the Clausius statement, you can rewrite this in a slightly different way. It says no process is possible whose sole result is the transfer of heat from a colder object to a hotter object, which means that you require additional work to be done so that heat can be transferred from a colder object to a hotter object. Now, this is the concept of a heat engine. In the heat engine, you have a source and a sink, and then there is a working substance, which is your working fluid. Okay, a certain quantity of heat is drawn from the hot source at a temperature T1. The quantity of heat is Q1, and then a certain amount of work is done by the working fluid, and then it rejects certain quantity of heat, which is Q2, to the sink. Now, what is the best heat engine that one can have? That heat engine is nothing but the Carnot cycle. The Carnot cycle says there are two isothermal processes. It consists of two isothermal processes and two adiabatic processes. Okay, that is your Carnot. Now, the heat engine with Carnot cycle can be described either in the PV diagram or a TS diagram. And you can see the PV diagram here. Okay, so you have a isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. So the area within this curve is now the work done by this particular cycle. The same thing can be represented as a TS diagram in which you can have isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. Okay. Now the heat is drawn in the zone of isothermal expansion and then heat is rejected in the process 3 to 4, which is isothermal compression. Okay. So the net work done will be equal to the area between the curves. Okay. Within the curve, within this cycle of operations. Okay. Okay. Now you can calculate what is the efficiency. I'm not going to the details of the calculation. The efficiency of the heat engine. What is the efficiency? Efficiency can be just defined by the work output to the heat input. What is the work output done by the gas to the heat input? Now the work output in this case, you can calculate what is the area enclosed within this curve. We can finally come across the relation. Heat efficiency is equal to the net work done divided by the heat absorbed, which is equal to Q1 minus Q2 divided by Q1, or in other words, it is T1 minus T2 divided by T1. Okay, that's the formula what you get. Okay. Now let's come to the concept of refrigerator. What is a refrigerator? Suppose we reverse the cycle of operation of a heat engine, we get what is called a refrigerator cycle. Now the performance of the refrigerator is expressed in terms of the coefficient of performance, or it is known as COP. Okay. You don't call it as efficiency, you call it as coefficient of performance. In a refrigerator, heat is removed from the low temperature source and thrown into the high temperature sink. Okay. Now, there are two possibilities. You can think of, your end result, what you want is the removal of heat from a low temperature source. Then the desired output in this case, is the removal of heat from a low temperature source. This is now called a refrigerator. On the other hand, if the desired output is the transfer of heat to a high temperature sink, it is known as a heat pump. An example for this could be, for example, a house in a winter season abroad, for example, wherein the heat is added to a house from the outside, so using a certain working cycle, and the desired result in this case is to keep the house warm, to maintain the temperature of this house to a high temperature. Now, such a process is called a heat pump. This is known as a heat pump, whereas the previous one is known as a refrigerator. Okay. Now we can estimate the coefficient, the coefficient of performance of a refrigerator cycle exactly in the same way as we did in the case of heat engine. Now the processes are the opposite. Okay. So we are starting with AB isothermal compression, okay, adiabatic expansion, isothermal expansion, adiabatic compression. So now in this case, the desired result is the removal of heat, and therefore Q2 divided by Q1 minus Q2 is the so-called COP. Okay, it is written as here as eta in this diagram, but please remember this, you have to call it as COP. Okay, or in other words, it is T2 divided by T1 minus T2. Okay. Now, we can very clearly see here that if I want to have a desired output is the removal of heat from a low temperature source, I need to add work to the system. That is, work has to be added to the system so that it is possible to remove this heat. Okay. Now, you can also see very clearly the Carnot cycle is the one which will be the best cycle which can produce this this is possible to have the best operating cycle using the Carnot cycle. Okay. Now, you can very clearly also note, suppose I want to reach absolute zero of temperature, then T2 should be equal to 0 and T1 can be room temperature or whatever temperature you would like to select. So now COP for such a process will be COP is equal to 0 divided by T1 minus 0. In other words, it is equal to 0. So it is not possible to reach absolute zero of temperature because the coefficient of performance of such a cycle is equal to 0. Okay. So it clearly violates your it clearly tells you that you cannot reach absolute zero of temperature. Okay. Now, this diagram is simply telling you the coefficient of performance for refrigerator in comparison with the coefficient of performance of a heat pump, right? In the refrigerator case, COP is equal to TL divided by TH minus TL, whereas the COP of heat pump is TH divided by TH minus TL. Okay. Now, this is shows you how the household refrigerator was working. So you start with a freon gas in the compressor, which is initially at a pressure of, let us say, 800 kilopascal at about 60 degrees. You initially at, let us say, at room temperature, after compression, it becomes 800 kilopascal at 60 degree. Then this gas, compressed gas, enters a condenser at the backside of your fridge, okay, where it loses its heat content as well as it becomes condensed, okay. And once it condensed, it can become a liquid as well. And then it falls into the same 8 bar pressure is there, or it can be slightly lower. And it passes through an expansion wall where the pressure drops as well as temperature drops. It becomes expanded liquid and vapor situation where at 120 kilopascal at 25 degrees centigrade. And that cold fluid passes over the evaporator, which is inside the fridge, wherein your objects are all kept inside for cooling, and they cool the object and gets warmed up, then come back as 120 kilopascal vapor at minus 20 degrees and then enter back into the system, okay, into the compressor. It warms up and come back to that room temperature into the compressor. Okay. Now, let me briefly discuss about entropy. The second law states that processes occur in a certain direction, not in any direction. It leads to the definition of a property called entropy, which we already discussed earlier. It is a quantitative measure of the disorder of the system. Well, the definition of entropy keeps changing with the time. There are newer versions of concepts of entropy coming up. Okay. Entropy can also be explained as a measure of unavailability of heat to perform work in a cycle. That is, they call it as exergy. Okay. Now, in any case, a mathematical definition of entropy is more meaningful. The change in entropy during a reversible process is defined as ds is equal to dq by t. Okay. The process is supposed to be reversible. That means if a certain quantity of heat is added to your system at a particular temperature T, there is a change in entropy ds. ds is equal to dq by t. If you integrate from one position to another position or one state to another state, then the change in entropy will be S2 minus S1 will be equal to integral one process of 1 to 2 dq by t. Okay. Now, if you consider a reversible adiabatic process, the change in entropy is 0. Okay. In other words, the initial entropy is the same as the final entropy, or S2 is equal to S1. The reversible adiabatic process is called an isentropic process, right? Okay. The entropy change and the isentropic relations for a process can be summarized as follows. For pure substances, you can write delta S is equal to S2 minus S1. The units will be so many kilojoules per kilogram Kelvin. And for isentropic process, obviously, since delta S is equal to 0, it is S2 is equal to S1. For incompressible substances such as liquids and solids, S2 minus S1 will be the C average specific heat into T2 by T1. Okay. And similarly, for isentropic process, T2 is equal to T1. For gases, for example, there are certain expressions available for assuming they have constant specific heats, and S2 minus S1 is equal to CV average ln T2 by T1 plus R ln V2 by V1. Or also you can rewrite it as S2 minus S1 is equal to CP average ln T2 by T1 minus R ln P2 by P1. For an isentropic process, there are some relations which are given as T2 by T1 is equal to V1 by V2 to K minus 1. Okay, K is nothing but your gamma. Okay, and T2 by T1 is equal to constant equal to P2 by P1. So gamma minus 1 by gamma. Ratio gamma is the ratio of specific heats. Here it is given as K. Okay, P2 by P1 is equal to constant equal to V1 by V2 to the power K. Right? So these are some other relations which we have. Now, I will just discuss two problems. Okay. Now, let's consider one problem. The problem is a cylinder contains 12 liters of oxygen at 20 degrees centigrade and 15 atmosphere. The temperature is raised to 35 degrees centigrade and the volume is reduced to 8.5 liters. What is the final pressure of the gas in atmosphere? Treat this as ideal gas. So we have to use the formula P1V1 is equal to nRT1 or P2V2 is equal to nRT2. So you can write, so in other words, P1V1 by T1 equal to P2V2 by T2. So if you do that, then here 1 and 2 are represented as final and initial. So the PF is equal to PI TF VI divided by TI VF. Okay. So if you would substitute the temperatures which are given in centigrade converted to Kelvin, you introduce the relation, the expression, all the data can be introduced here. So PF would be equal to 15 atmosphere into 308 into 12 liters divided by 293 into 8.5. That is approximately 22.22 atmospheres of will be the final pressure. Okay, 1 mole of oxygen treated as an ideal gas. It expands at constant temperature 300 Kelvin to an initial volume of V1 of 12 liters to a final volume of 19 liters. How much is the work done? Okay, so we have a pressure and then the volume. So the initial pressure is 20 bar. Sorry. Am I right? No. Initial pressure is 2 atmosphere and the final pressure is some value, we don't know, F. Okay. And the volume changes from 10 liters to 20 liters. So we have to calculate it is expanding at a constant temperature of 3 is equal to a temperature of 310 Kelvin from initial volume to a final volume. How much is the work done? Okay, at constant temperature. So the temperature is constant. So it is now expanding like this. So we have to calculate what is the work done in the process. Work done is equal to nRT into ln VF by VI. So 1 mole of gas, 8.31. So R value we have substituted. And then 310 Kelvin into 19 by 12, ln of 19 by 12, which is 1180 joules. So the expansion is graphed in the PV diagram. The work done by the gas during the expansion is represented by the area beneath this curve. That is your W. Okay. So you can show that if the expansion is now reversed with the gas undergoing isothermal compression from 19 liters to 12 liters, the work done in this case will be minus 1180. Thus, that an external force would have to do it In other words, work has to be done on the gas to compress it, right? That's what we see. I think I have more or less completed the presentation. I thank you very much for your patient listening, and thanks a lot. Have a nice day. All the very best to you.